Hi there, my name is Thermodynamics. I'm going to be doing a presentation on thermodynamics, basics for process modeling. So what is a thermodynamic model? A thermodynamic model, sometimes called vapor-liquid equilibrium model, is a method to calculate phase separation for a mixture at a given temperature, pressure, and composition. These models are also referred to as K models because relative volatility, Ki, can be determined by vapor-liquid equilibrium calculations, Ki, which is equal to Yi over Xi, where Yi is the vapor phase mole fraction of component I, and Xi is the liquid phase mole fraction of component I. Most K models are for vapor-liquid separation. Some can perform equilibrium calculations for two liquid phases. So mostly the simulation softwares which are capable of doing two liquid phases are the commercial ones like Aspen, Chemcad, and Formex. Selecting the right thermodynamics model. The story about thermodynamics can hardly be a simple one. If somehow could be a simple one, and the world be ideal, we would have only one nice equation that is nice to describe any system. But in contrary, we have so much equations because the world is not ideal, right? But in an ideal world, things are far from that. When developing a process model, a chemical engineer should have enough knowledge to be able to choose from a large number of thermodynamic systems. Chemical engineering as a field is progressing day by day, and as a result of the number of thermodynamics equations and parameters is increasing with the aim to improve mathematical descriptions of different systems, which means you're trying to make these models more accurate, and yes, they increase in terms of numbers, right? So our knowledge becomes very important to selecting the most appropriate thermodynamics package. Take note, taking the wrong way while developing a process model can cause a huge waste of time and misleading results. It simply means that your simulation won't be able to predict whatever is happening within the real plant. So, which means it's just useless, right? Particularly important for reliable computations associated with separation operations. For example, distillation, liquid-liquid extraction. This is because these are more rigorous as compared to simple applications like the pumping or compression. The choice of a thermodynamic package will have an impact on accuracy of your results. Are they able to predict the results from the plant, complexity of the calculation, and convergence, which means will your simulation come up with a solution? Most applications require only one set, but complex flow sheets may be modeled best with several. For example, if I'm modeling, a chemical plant with a distillation column, I'll use an activity. For example, a Wilson thermodynamic model for the distillation column, but let's say I'm also pumping some water somewhere else. I'll use the steam table for that because for water, the steam table is more accurate as compared to other thermodynamic models. Different types of K models. Different mixtures have different dominating behaviors, and different models have been developed to fit these behaviors. Choosing the appropriate K model for a particular mixture requires engineering judgment to review the chemicals, type of mixture, and range of conditions, which are temperature, pressure, and concentration. Start by identifying the solution behavior for the mixture and select the K model category. There are many categories of these thermodynamic models, and I'll look at them each one by one as I go down with my presentation. Then choose a specific model from within the category and validate results, because these thermodynamic model categories, you have many models within. So you first choose the general category, then you choose a specific one. Then you need to validate your results to see how accurate they are. Different types of K models. The first one is the ideal gas model, which you can use the Roth law or Henry's law, depending on your concentration. So at ambient conditions, many light gases approximate ideal gas behavior. For example, air at room temperature and pressure. At elevated pressure or lower temperature, the ideal gas model is less accurate. The ideal gas model becomes valid at high pressures near critical points and for mixtures of molecules with moderate difference in molecule size. For example, combustion gases at high temperature and pressure. You usually find this at the exhaust gases of a steam boiler. The second one is the equation of state. So the primary role of equation of state is that they can predict thermodynamic properties at any conditions of temperature and pressure, including the critical region. The Saw, Fredlich-Kong, and Peng-Robson are the mostly commonly used equation of state models for raw gases. Equation of state calculations are based on pure component parameters such as the normal boiling point, critical temperature, critical pressure, and acentric factor, which means you need these parameters before you can use an equation of state. It is important to have accurate values for these parameters if you intend to use an equation of state. They are the best choice when modeling compressed gases and compressors. Hydrocarbon mixtures, light gas mixtures, and atmospheric gases are well modeled by an equation of state. And I'll add also in the crude oil distillation, they usually use the Peng-Robson, which is an equation state, for modeling their process. Some equation of state are well suited to high pressure systems and can be used to model supercritical carbon dioxide compression. An equation of state is also often used to model gases and hydrocarbons at high pressure. They are less reliable when the sizes of the mixture components are significantly different, or when the mixture is at the critical point of any of its components. I should add that though they are less reliable, if any of its mixture is at its critical point, they do better as compared to other types of thermodynamics models. So when you're at the critical regions, you should use an equation of state. These models also do a poor job of predicting the behavior of non-ideal liquids, especially polar mixtures like water and alcohols. Activity coefficient models, the type. These are appropriate for regular solutions, non-ideal liquids, polar liquids, and general ideal vapor. Non-random two liquid, which is the RTL, and the Wilson models are the most frequently used. The primary role of solution models is to provide semi-empirical models which have a greater degree of flexibility than equation of state models, owing to the greater number of adjustable parameters and their judicious choice, such that both magnitude and skewness of the free energy curves can be accurately tuned. These models focus on the behavior of the liquid and assume ideal gas behavior, but advanced users sometimes use an equation state to fine-tune the vapor fugacity. Activity models are used for non-ideal liquid solutions. those do not conform to Rod's law, which they can either have a positive deviation or a negative deviation, depending on the characteristics of the available mixture. The molecules have drastically different sizes. Binary interaction parameters models calculate activity from binary interaction parameters which are fit to data. For the most accurate results, you need binary interaction parameters that have been regressed from empirical data, which means for you to use these models, you need to have some empirical data. So you first do experiments or go to literature and find some empirical data and come and use it to fine-tune these models. Predictive activity models are based on general molecular structure. These also fall under the activity coefficient models, right? Predictive models cannot be used for all chemicals because the behavior of all subgroups is not yet understood. And this is a master's level project idea. You try to understand these subgroups which are not understood, right? Some activity models can be used to calculate or predict liquid-liquid equilibrium, and these only can be found on the commercial simulation packages. Special modifications can be used for electrolytes, polymer systems, and solid-liquid equilibrium. The accuracy of activity models depends on the quality of the regressed data. So if you have some empirical data, then these activity models becomes more accurate. A binary activity parameter model needs binary interaction parameters that were regressed for the chemicals in the system being modeled. A predictive model requires that group interaction parameters be available for various subgroups of a chemical structure. Otherwise, you won't be able to use it. If you use it, then it will give you inaccurate results. If you want to use an activity coefficient model but do not have binary interaction parameters, consider regressing them from data or using a predictive subgroup model. Systems that are well developed or modeled by activity models include mixtures of water and ethanol, two liquid phase mixtures such as water and toluene, and the ethyl acetate water system, which exhibits a homogeneous binary isotope, a heterogeneous binary isotope, and one ternary isotope. Systems that are not well developed by activity coefficient methods include light gas mixtures. These are gases which have a molecular weight which is less than that of air, for example, nitrogen. High pressure systems, hot combustion gases, and alkane mixtures. The fourth one is the combined and special purpose models. Advanced models combine the concept of activity with an equation of state. The most popular of these is the predictive Friedrich-Kohn or PSRK model, which often works well for systems in which the vapor is a real gas and the liquid is a non-ideal or polar. So you're using the activity thermodynamics model in conjunction with the equation of state. Special purpose models may use an equation state or activity model that is modified to fit one particular system. You can also use that as a project idea for master's level. If you have a particular system which is not yet studied, you can go ahead and use that as your master's level topic. The MOA model, for example, modifies the universal functional activity coefficient UNIVAC model to fit the water, formaldehyde, methanol system. This is also another master's project idea. If you have a system which is not studied yet, you can also fit it using this uniform model, right? These methods tend to compete with the hydrogen bonding models in the sense that they enhance accuracy for non-ideal solutions at high temperatures and pressures, e.g. the modified urine vital MHV method and the Wong-Sandler mixing works. They also tend to be more efficient computationally than the hydrogen bonding equations of state, e.g. the SEFT or the ESD. The fifth one is the aqueous electrolyte system models. Rigorous electrolyte models can model dissociation, its of solution, and boiling point elevation. And because these models account for ion interactions, they can also represent pH. Electrolyte models are meant to be used for aqueous systems that are at or near atmospheric pressure, which means they are more accurate at these regions. If you have an electrolyte system, select a customized electrolyte model. If your simulator does not have electrolytes package, it might have a simplified module that can model some of the industrial important reactions, such as gas sweetening with caustic. Keeping the right way when doing a simulation. So I'll go on how you keep the right way when doing a simulation, step by step. So the first step is overview of the process to be modeled. So overview of the modeled process refers to a review of the component list and expected working conditions. Are components liquids or gases? Are they mostly hydrocarbons? Is there any specific components such as hydrogen sulfide, for example, etc.? When looking into temperature and pressure characteristics, it should be noted if the expected temperatures and pressures are around atmospheric or are they significantly higher. Some simulation programs may suggest what thermodynamic system suit best for a defined component list. However, it is always good to review the default selection. Don't just take whatever is suggested by a computer application and run with it without using the common sense. If there's no any suggestion or we do not want to follow it, then we should follow some general guidance based on our system definition and components list. Step 2, selecting the thermodynamic model. When faced with choosing a thermodynamics model, it is helpful to at least have a logical procedure for deciding which model to try first, and a decision tree is often used. For non-polar fluids, an equation of state may suffice. For polar fluids, a fitted activity coefficient model is preferred, possible in combination with the Hayden or Cornell method, or in combination with some other equation of state for the vapor phase, for example, the Peng-Robinson. This approach can often provide satisfactory predictions as long as the pressure are 10 bars or less. Predictions by this approach should be checked against literature data to the greatest extent possible. So this is the decision tree which I was talking about. So you start by classifying your components in the process. You know, are they in gases? Are they non-polar, associating, solvating, or electrolytes? I'll go through examples on how to use this decision tree. For example, for benzene, toluene, and xylene, and assuming we're working at 8 bar. all gases? No. We know that benzene and toluene and xylene, they're liquids, right? Are they all nonpolar? Benzene is nonpolar. Toluene is nonpolar. Xylene is nonpolar. So yes. So we'll try penroxone or solve Rutledge-Combe or the API, right? Okay. What about for water and sodium chloride? All gases are nonpolar, of course, water and sodium chloride. They are not gases, but both of them, they are polar, right? Water is a non-electrolyte. It doesn't conduct electricity. It doesn't dissociate, right? But sodium chloride is an electrolyte because it completely dissociates from sodium cations and the chloride anions in water, right? So it is an electrolyte. So yes, electrolytes, yes, you come here. So we'll try the NRTL, the pizza, the Promly, whichever has all the binary interaction parameters. So you open and check it. That particular software, simulation software, has those binary interaction parameters. What about for the third one? It's hydrogen, methane, benzene, and toluene. Okay. Hydrogen is nonpolar. Methane is nonpolar. Benzene is nonpolar. Toluene is nonpolar. They're all gases. No, of course, we know hydrogen and methane. They are polar stone and pressure, but benzene and toluene, they're liquids. But they're all nonpolar, right? So we can use try the pairing props on the SRK or the API. Last but not least, we'll look at water and propanol. All right. All gases, of course, water and propanol, we know they are liquids at STP. Water, of course, is polar. Propanol is polar too. All alcohols are polar, by the way. Are they electrolytes? No, of course they are not. Both of them. Then, so you come here, any gases like ammonia, carbon dioxide, or is the pressure above 10 bars? We know there are no any gases. So we go this way. Binary interaction parameters, all known. So here, that's when you go and open your simulation software and see if there are binary interaction parameters available, for water and propanol. And if it's yes, you use the NRTL, the Uniquark, the Wilson, the Vanla, whichever is all binary interaction parameters, they'll give you same results. If not, then you try the Unified. If possible, estimate the BIPs for missing components only. So that's how you use this decision tree. You can keep going down as long as the answer is yes to this question, right? So a process that is otherwise fully optimized in terms of equipment selection, configuration, and operation can be rendered essentially worthless if the process simulator is based on inaccurate thermodynamics models. So selection of the thermodynamics model is the most paramount stage in process simulation. Once you do that right, everything else that follows will be simple and easy and accurate. Select an appropriate fluid package for the following systems. I already showed you how to use a decision tree on these systems, so I'll go over it again. If there are no experimental data for one of the binary systems in this event, then Unified can be used to generate pseudo-data that can be used to predict the Gibbs excess energy for that binary. And these pseudo-data can be used to regress Uniquark or NRTL parameters if desired. If you need to predict phase behavior over a broad range of conditions, based on a few data in a narrow range of conditions, A hydrogen bonding equation might provide more reliable leverage in light of its clearer connection with the physical chemistry in the solution. If you're dealing with compounds that dissociate electrolytically, for example, salts, like sodium chloride, or potassium iodide, or associate strongly and specifically in solution, then it will be probably be necessary to apply a simultaneous reaction and phase equilibrium approach. These kinds of systems are common in gas strippers for compounds like carbon dioxide, hydrogen sulfide, and amines. For these systems, it is especially important to check your correlations against experimental data near the conditions of your specific interest, because also a reaction is involved, so the calculations becomes more complex and more rigorous. The third step is continue with the model development. Upon the selection of the thermodynamics model, you can continue with your work. In this case, if you're facing any problems related to model accuracy or convergence, save your work, do another copy of your simulation, and try to use another thermodynamic model for your simulation. Obviously, use a similar thermodynamic model. If you're using an equation of state, you choose another equation of state. Step 4, validating the thermodynamics model. You're trying to find out how accurate does it predict, whatever is happening within the plant, the results from an equipment from the plant. Once you have selected a K model, it is crucial to validate that it will accurately model your system. Sometimes a model that should give good results does not fit a particular mixture. It might be missing parameters for a chemical. System conditions might be outside its applicability range, or the model type might not be appropriate for the system. So compare the results to results from similar models and to experimental data for your system. So how do you do that? First, you need to verify physical property data. If you're using an equation of state, make sure you have the critical temperature, the critical pressure, the normal boiling point, and the asymptotic effector. These must be accurate, right? For binary interaction parameter activity model, accurate normal boiling point, vapor pressure as a function of temperature, and binary interaction parameters between important chemicals are necessary. The binary interaction parameter pairs must be known or regressed from available experimental equilibrium data. Predictive activity subgroup models consider a molecule as the sum of smaller parts whose interactions are known. For this model type, verify that all the chemicals in the system are described by functional subgroup, because in the absence of binary interaction parameters or subgroups, the behavior of the chemicals will be similar to that of an ideal liquid. This is the worst case scenario. It will make your results garbage. They are not accurate at all. The second way, inspect the model results. So always inspect model results. An easy way to do this is to construct the TXY or the PXY plots for imported pairs of components. These are the components which are available at higher amounts. Right? Plot and inspect several TXY and PXY diagrams to validate that the model is matching your expectations. If you have these TXY and PXY from literature, see if they match the ones from your simulation software. Learn how to recognize azeotropes and second liquid phases on the diagram. Then you can draw these and inspect if your simulation is able to predict these azeotropes or the second liquid phases. If you know that the two chemicals in the mixture being modules form an isotope, plot the XY diagram to determine whether the simulator is calculating the isotope. If not, you know, it's not good for that application. Another option is to perform simple flash separations on the flowsheet to verify that the vapor and liquid separation conforms to your expectations. If you have selected an inappropriate model, the phase separation may obviously be wrong. If you're modeling existing equipment, try to match experimental observed data. For highly non-ideal systems, consider generating ternary binodal plots or residue curve maps. These steps can validate that you are not on the right path or send up warning flags that the model will not give realistic results. The third way is compare to similar models. Different models in the same category will typically give you similar results. If you're using the SRK model, for example, you can compare the results to those of other equation of state models. If you're using an activity coefficient model, compare to UNIVAC, modified UNIVAC, and the PSRK results. If similar models do not give similar results, investigate the differences. Ask yourself, why is that happening? The fourth way is compare to external data. To be certain the model selected fits your system, it is necessary to compare the modeling results to data. Even a few data points can be valuable, either to validate the model or adjust it to a better approximate reality. If you do not have vapor-liquid equilibrium data, search the literature. This is often much more affordable than generating new experimental data, though it's less accurate. If multiple sources of data are available, there will be disagreement among the data sets. Then how do you choose which data to use? So the best source of data is typically operations data from your plant. So if you have this one, it takes priority. Pilot plant operations data are the next best, followed by the laboratory data and then literature data. So you should resolve to go into log for literature data when you don't have this data from the plant itself, or if you don't have data from the pilot, or you cannot do experiments. Then that's when you can go to literature and look for information. Literature data are better than estimated or guesstimate data. Trust the very skilled chemist. It's more reliable than an expensive online analyzer. That's where, as an engineer here, you need to accept that you do not know everything and trust the chemist, because they spend most of their time in the lab. They are familiar with reactions. They can have a better guesstimate. Try to simulate the same conditions in the model as the conditions at which your data points were obtained, and inspect how closely the model can match them. So if you get data from the test book, try to enter that information in the simulator and see if there's agreement. If not, which means the simulator will not be able, to accurately calculate the results for your particular application. If you have binary XY data, plot it against the XY diagram created by the simulator. So you get this XY data from literature or experiments, right? You plot it against the XY diagram created by the simulator and see how they match. If you have a multi-component data, try to model it with flash separation. For example, if you have a blend data for the liquid composition from a reboiler, assume that this liquid is at its bubble point. Enter the composition into a stream simulator and specify pressure and a small vapor fraction for a flash calculation. If the calculated temperature and liquid compositions are not close to your plant data, the model might not be appropriate. Find relevant data. Use the material safety data sheets from chemical manufacturers. So of course, they know much better whatever product they are selling, right? Use the NIST chemistry webbook. Use the AI Chem e-library. This is only for members, so you need to subscribe to them. Use the DIPPR, which is the Design Institute for Physical Properties Research database. You can find it online too. Use the DTherm database, which can be found online too. Thank you so much for watching. And if you have any queries or questions, please contact me on my email address, tubaspan@gmail.com. You also like, subscribe, and comment to my YouTube channel. Also, consider clicking the link on the description to support my t-shirt sales business. On the next presentations, I'll be doing some nice simulations. So if you're interested in those, keep on coming back to my YouTube channel and looking for those. Most probably for the next one, I'll do a simulation on distillation. Thank you so much, Billy. Bye.